chapter 5. So electric current is defined as the rate of flow of charge, or the amount of charge passing through an area in a given time interval. So current, you could say current equals charge divided by time. So delta Q here stands for charge, delta T stands for time. Now, the direction of conventional current is taken as the direction in which positive charge moves. Okay, so if they ask you what's the difference between electron current and conventional current, you should be able to state that the conventional current is taken as the direction in which positive charge would flow or would move. Whereas electron current is the direction in which negative charges will move. And you may ask, why talk about conventional and electron current? The reason is simple. Before electrons were discovered, the pioneers in the field of electricity believed that electricity was conducted by the movement of positive charges. So they simply didn't know that negative charges existed. But long after electrons were fully understood and discovered, society decided to maintain the old convention that current goes in the direction of positive charges. Okay, so if you're given a simple electric circuit, this is the positive terminal, this is the negative terminal. So the direction of conventional current so the blue arrow indicates how conventional current will flow. And that is what is used today. In reality, electrons move from the negative plate to the positive plate. So electrons go like this. That's the electron current. The blue is the conventional current. And note that current is denoted by the symbol I. Units. The unit of current is the ampere. So by definition, 1 ampere is equal to 1 coulomb per second, because I equals delta Q over delta T. So I is in amperes, charge is measured in coulombs, time is measured in seconds. So one ampere is 1 coulomb per second. The drift velocity is the average speed at which the charges move. So if we draw an exaggerated cross-sectional area of a conducting wire, so inside this wire, you have charges drifting along based on the the potential difference across the conductor. Okay, so the relationship between the current and the drift velocity is this. So the macroscopic current, this is what you would measure using an electric measuring device like the ammeter. This will be, or this is related to the microscopic charges by the equation N, Q, A, V sub D. So N is the density of the charges. That is the number of charge carriers per unit volume. Q is the charge carried by one of the charge carriers. For the electron, that will be 1.6 times 10 to the minus 19 coulombs. A is the surface, the cross-sectional area. So the cross-sectional area, this is A. And V sub D is the drift speed or the drift velocity of the charge. So you should be able to calculate current if you're given these parameters, the charge density, Yeah, does someone have a question? Scott, do you have a question?
No.
Okay, then make sure your line is muted. Okay, so the macroscopic current I is equal to the charge density N times the charge carrier Q times the area times the drift velocity. Area is simply equal to pi r squared. If you know the radius of the wire or the diameter of the wire, you can calculate the radius and then the area. And electrical signals travel at speeds about 10 to the 12 times greater than the drift velocity of free electrons. Okay, so that's the basics of electric current. That's the summary of the section on electric current. Now let's look at Ohm's law. So Ohm's law basically depicts the empirical relationship between voltage, resistance, and current. So from experiments, it has been determined that the current flowing through an ohmic device is proportional to the voltage. So this equation could also be written as V equal to R times I, or I times R. So it's still the same relationship. It's just a question of rearrangement. So basically in an ohmic material, the voltage and the resistance are proportional. So if you plot the voltage as the function of current, you get a straight line, and the slope of that straight line is equal to the resistance. And we know a straight line has a constant slope. So materials that behave like this are classified as ohmic materials, whereas non-ohmic materials will be the ones where the voltage and the current do not have a linear relationship. So let's say the voltage current behaves like that. So this will be a non-ohmic. Basically, that means the resistance is not constant. And this is common in certain materials. As temperature increases, the material becomes more and more resistive, whereas in some, the material becomes more conducting. So that's the difference between ohmic and non-ohmic. It's one of the learning outcomes. So you should be prepared to differentiate between ohmic, an ohmic material, and a non-ohmic material by describing in words or by using a graph. An ohmic material will have a linear graph between voltage and current. A non-ohmic material will have a curve. An ohmic material has constant resistance. A non-ohmic material has non-constant resistance. Now the units for resistance is the ohm, the omega symbol, that's a Greek symbol. And 1 ohm is equal to 1 volt per amp because resistance will be equal to voltage divided by current if we transform this equation. So that means ohm, which is the unit for resistance, is equivalent to the volts, unit of voltage, divided by the amp, which is the unit of current. And so you should be familiar with those units. 1 volt is equal to amps times ohms because V equals I times R. So 1 volt is equal to 1 amp times 1 ohm. So be familiar with these units and the derivation of other units from here. Let's talk about resistivity. So basically, resistance is like the degree to which a material impedes or blocks the flow of charges. Okay, and if we use the analogy of a pipe, so a wider pipe will allow water to flow through more easily. So let's say we have 2 pipes. I have a tiny pipe and I have a larger pipe. In which of these pipes will water flow through more freely? Obviously, the second pipe, the one with a bigger cross section. Okay, so the ease or the difficulty with which water flows through the pipes could be compared to the resistance in a wire. So basically what we say here is a wire that has a larger cross-section area will have a low resistance, and one with a smaller cross-sectional area will have a high resistance. Also, a shorter pipe will have less resistance, and a longer pipe will have more resistance. So if we combine all these factors, we find that the resistance of a wire is proportional to its length. The longer the wire, the more resistance the charges will experience. The shorter the wire, the less resistance. And the resistance is inversely proportional to the area because as area becomes larger, resistance becomes smaller. So combined together, we'll have rho times L over A. So this basically says R is proportional to L and is proportional to 1 over A, or inversely proportional to A. The constant of proportionality is called the resistivity of the material. So this is unique to every material. just like density is unique to every material. Copper has all materials, all wires made from copper will have the same resistivity. They may have different resistances depending on the length and area, but all wires made of iron will have the same resistivity, and all wires made from aluminum will have the same resistivity. So what you need to note is the resistance of any wire is directly proportional to the length, but it's inversely proportional to the area. What this means is that as the area increases, you have lower resistance. As the area decreases, you have higher resistance. But for the length, as the wire becomes longer, you have more resistance. As the wire becomes shorter, you have less resistance. One could even expand this further to say that since R is proportional to 1 over A, but A is equal to pi R squared, then you could say R is proportional to 1 over R squared, because A is pi R squared. So you could determine the resistance just by adjusting the radius of the wire. So if you double the radius, for instance, then your resistance should change by a factor of 1 over 2 squared. So 1 over 4, 1 over 4. So if you double the radius, your new resistance will be 1/4 the original resistance. Okay. If you quadruple the resistance, the radius, then the new resistance will be 1 over 16 times the original resistance. So let's say a wire has a resistance of 20 ohms, and the problem says find the new resistance if the radius is doubled. So from our analysis, since R is proportional to 1 over R squared, so doubling means multiplying by 2. So 1 over 2 squared is 1 over 4. So that means the new resistance will be 1 over 4 times the old resistance, so which is only 5 ohms. So if we wanted to reduce the resistance of a wire from 20 to 5, all you need to do is manufacture a new wire of the same material with 2 times the radius or 2 times the diameter. Conversely, if we had halved the radius, what will happen? Can somebody respond? If the radius is halved, what will happen?
Would it be shorter resistance?
By what factor?
It will increase by 4.
It will increase by 4. That's exactly correct. So again, R is inversely proportional to 1 over R is inversely proportional to R squared. So if we introduce a factor of half here, half R, and then we square it, we end up with 1 over 1/4 R squared. What is 1 divided by 1 over 4? 1 divided by 1 over 4 is
4.
4. Okay. So 4 over R squared. So as you can see clearly, if you have the radius, then the resistance actually increases 4-fold. So if the original resistance was 20, the new resistance will be 20 times 4. which is 80 ohms. So if you want a wire with higher resistance, you need to make it thinner. You need to reduce the radius of the diameter. If you want the wire to have less resistance, then you need to increase the diameter. Okay, so this we've done this. This is not the first time you're saying something like this. Remember when we did Coulomb's law, F equals K Q Q2 over R squared. We did problems where you had to determine the force if you increase the separation, if you double one charge, or you triple one charge, and so on. So this is exactly the same kind of analysis. And you should be prepared to do this, you know, for any physics equation. Okay. Resistivity, even though resistivity is constant for a given material at the given temperature, if you change the temperature, resistivity does depend on temperature. So this equation shows us how the resistivity depends on temperature. So the rho sub O is the resistivity at room temperature. And then the other resistivity, this is the regular resistivity at any temperature. Okay, so this is room temp, and this is any temperature. And delta T, of course, is the change in temperature. Okay. And alpha is a constant. It's called the temperature coefficient of resistivity. And in the book, in table 5.2, you can see all the values of alpha. In table 5.1, you can see all the values of rho. So rho is the resistivity. It's pronounced rho. And then alpha is the temperature coefficient of resistivity. And basically the resistance follows the same expression, okay? The same expression in this box. Resistance at any temperature equals the resistance at room temperature into 1 plus alpha times delta T. So delta T is just T minus T of, so the regular temperature minus the room temperature. That's the change in temperature. And then electrical power and energy. So the power supplied by a source or the power dissipated by a device is simply the product of the current and the voltage. So P equals V times I. And we remember from Ohm's law, V is equal to what? From Ohm's law, V is the same as
IR.
So IR. This is IR. So if you plug in IR here, you get IR times I, which is the same as what? I squared times R. Okay. And then remember, I from Ohm's law is V over what? from Ohm's law, I is the same as V divided by
R.
R. So if we substitute I by V over R, we end up with what? With V over R squared times R. So this is the same as V squared over R squared times R. So this R will cancel this one R, and you end up with V squared over R. Okay? So we could say that P equals V times I equals I squared times R equals V squared over R. All these three equations are equivalent. So it depends on what is given. Okay. So depending on what is given, you may be able to use one equation or the other. So I squared times R, V squared over R, I times V. They're all equivalent. Okay, and you can read section 5.5 and up to 5.7 for completeness. But this sections 5.5 to 5.7 will not be on your test or the final exam, but you need to be aware of the difference between alternating current and direct current, average power, root mean squared value, and so on. You need to be familiar with those terms. Okay? You cannot say you've completed this class if you're not aware of any of these terms. So I'm not saying that this is not important. I'm just saying I will not test you on this, but I do require you to review this section, but don't spend too much time trying to master everything. Just read it for information purposes to be aware of, alternating and direct current, as well as the various electrical hazards in the human body and so on. So from here, we have the conceptual questions. And then if you keep scrolling down, you go to the section on problems and exercises. This is where you should really focus. So for instance, what is the current in milliamps produced by the solar cells of a pocket calculator through which 4 coulombs of charge passes in 4 hours? Okay, so in the few remaining minutes, let's do a couple of these exercises. So let me get any suggestions from the class. How would you approach this kind of problem?
Would you convert the hours to seconds first?
Okay, that's correct. And then after that, what will you do? Do you have a touch screen? Are you connected from a tablet?
No, my phone.
Okay. I was going to say you can write. I can give you guys the ability to write into the whiteboard if you have access to a touch computer or tablet. But just go ahead and tell me how you will proceed. So you say you convert to hours, and then what will you do? The question is open to the whole class. Okay, what is the main, so let's do the conversion. So 4 hours is the same as 4 times what? What's the conversion? How many minutes do we have in 1 hour?
60.
So 60 minutes, 1 hour, and then what?
Seconds.
60 seconds in 1 minute. Okay, so the minutes will cancel. The hours will cancel. So 4 times 6 times 6, what is that?
I got 14,400 seconds.
Okay, so 14,400 seconds. So that's the time. Okay, so what do we do from here?
Find the amperes.
How?
Divide the charge by the seconds.
Okay, so tell me the equation to write. Q or I equals
Q over T. They change the Q over T.
okay, changing Q over T or just Q over T, and Q here is
4.
what? That's your
4.
Q, and that's your T, right? So
Yes.
4 coulombs divided by 14,400 seconds, and this is what? Everyone should be working on their calculator at this time. Okay, so what is the value? Okay, it's 2.778 times 10 to the negative 4. Okay, what's the unit?
Ampere.
Okay, you can have coulombs over seconds or amps. Okay, and this is the same as 0.277 or 278 milliamps. Okay, so you can write this as 0.2778 times 10 to the minus 3 coulombs per second or amps. But 10 to the minus 3 is milli. Okay, so if you see it written in either format, don't be confused. It's exactly the same thing.